Thank you very much, and I would really like to thank the organizers for the opportunity to speak in this conference on asymptotic properties of infinite groups. Probably the way this topic fits into the conference is that I'm going to talk about asymptotic properties of group orbits, which is a very, I would say, basic topic in ergodic theory, and as we shall also see, in Diophantine approximation. So before I start, I would like to say that everything I'm going to talk about is based on joint work with Anish Ghosh and Alex Gorodnik. And I would like to start with a few very concrete examples of the kind of results that are going to appear a little bit later. So let G be an algebraic subgroup of SLN, F. For F equals R or C or QP, the field can be really quite general. And we will also consider subgroups of the affine group, SLNF, semi-direct product with Fn, which we typically view as a subgroup of SLN plus 1. And we consider a lattice subgroup of G. Gamma is a lattice subgroup of G. We fix a norm on Rn and Cn, and on the space of matrices, MnR and MnC. And in the local field case, we take the standard valuation on the field and the standard maximum norm on the linear space Fn and on matrix space MnF. So this is all very simple. And now consider an affine subvariety V in Fn, which is invariant and homogeneous under the G action. So this is a transitive G space. There is a certain stability group H, and we put ourselves in a situation where we have an affine variety embedded in linear space. And we assume that almost every gamma orbit is dense in V. This is going to be a very, very robust assumption, and it's not going to cause any problem whatsoever. And basically, what we would like to do, we have that almost every orbit is dense, and we would like to quantify this notion. And so we restrict the norm chosen on Fn to V. And we consider the Diophantine inequality, the norm of gamma x minus x naught less than epsilon, with an element gamma in gamma satisfying the norm bound. The norm of gamma is less than a constant b times epsilon to the minus zeta. So the norm bound on gamma is a power of 1 over epsilon. And suppose that this inequality for some pair x, x naught in V can be solved for all sufficiently small epsilon by gamma in gamma satisfying the stated norm bound with some constant b. So the point is that epsilon goes to 0, and therefore you have to take elements in gamma which have norm larger and larger. But you have a certain bound on how far you have to go. So you can affect this approximation process at a certain level of efficiency, which is given by the size of this zeta. And define the Diophantine approximation exponent kappa xx naught as the infimum of zeta, such that the foregoing inequality has a solution with the properties stated. So if, in fact, we have such a finite zeta, then we consider the infimum, and we call this infimum the Diophantine approximation exponent. So far, this is just a definition. And we would like to understand this exponent and compute it. So kappa xx naught is a gamma times gamma invariant function. That's a very easy fact. And hence, it's almost surely constant when the action is ergodic. And of course, we're going, so if it's almost surely constant, it essentially has only one value, of course, if you're willing to delete a set of measure 0. And this value is the value that we are going to try to compute. Okay. So kappa depends on G, gamma, and V, but not on the norms chosen on Fn and MNF. Of course, it varies from orbit to orbit and from lattice to lattice, etc. So the only previous results we're aware of on the almost sure exponent kappa for actions of lattices in simple groups are as follows. There is a result of Laurent and Noguera from 2011 where they show that kappa is between 2 and 3, specifically for the lattice SL2Z acting linearly in the plane. And there is a result by Mokurant and Barak Weiss who give an explicit but not as sharp upper bound for kappa, but they consider arbitrary lattices in SL2R.
For which action is that?
This is the linear action. The linear action. Yes, there's going to be, okay. It'll become clear why I emphasize this point. Okay, so let us describe several examples where the best possible rate can be established, namely where kappa can be computed. So we consider the affine action of SL2Z semi-direct product Z squared on R squared, and we're going to consider planar inhomogeneous Diophantine approximation. This means okay, well, so we claim that here, in fact, kappa equals 1. And this gives the following explicit result in inhomogeneous Diophantine approximation in the plane. This means that for every x naught in the plane, and for almost every x in the plane, and for every epsilon sufficiently small, you can find integers a, b, c, d, m, and n, such that if you consider au plus bv plus m, comma, cu plus dv plus n minus the original vector u naught, v naught, then you have norm less than epsilon, and subject to the condition that the determinant a, d minus bc is 1, so you have a matrix in SL2Z, and the maximum, let's say, of these 6 integers is bounded by epsilon to the minus 1. Of course, there is this nicety with eta, but that's a feature of our definition. So, okay, this is sort of unavoidable in this theory. The take-home message is that kappa equals 1. But what it means practically is that you can solve this with epsilon to the minus 1 minus eta for every eta. Okay, so that's a typical feature of this analysis. So what you have here, of course, is the action of an element in SL2Z semi-direct product Z squared on the plane. So basically, we're looking at the orbit of the integral lattice in the affine action on the plane. And these orbits, they are dense, typically, almost all of them are dense, and they approximate points in the plane up to this efficiency. And you will not be able to produce kappa, which is less, you will not be able to do this with rate which is strictly less than 1. That's the meaning of best possible.
So eta equals 0 is not possible?
Sorry?
Eta equals 0 is not possible?
That's a very difficult question, and I don't know the answer. No, I mean, it's a feature of almost every argument in this analysis that you have this fuzz, you have this slack. Whether it's literally impossible, I don't know. But I do know that you can't go strictly less than 1. There could be, I mean, usually in Diophantine approximation, there is a whole wide world out there, and there can be powers of log, and which we all, you know, cover with this epsilon. Yeah. So, yeah, that's a second order question. I don't really know the answer. Yeah, I could say that in some situations, if you have sufficiently good estimates in some other problem that I will mention later, then you can replace the epsilon by certain powers of log. Yes, that is sometimes possible. Okay. Okay, so the upper bound on the size of the solution is optimal, and okay, so I emphasize that we're talking about the affine action rather than the linear action. That makes a very big difference in this case for the kind of arguments that we use. Now, let's also consider complex inhomogeneous Diophantine approximation. So we consider the affine action of SL2Zi semi-direct product Zi squared on C squared. And we can ask exactly the same approximation question. We have the orbits of gamma. And here, the exponent of Diophantine approximation for the gamma action gives a rate for inhomogeneous Diophantine approximation by Gaussian integers in C squared. And once again, the best possible rate is given here by kappa equals 1. And the same result holds for inhomogeneous Diophantine approximation in C squared by the Eisenstein integers contained in Q, the square root of -3. However, for the corresponding approximation result using algebraic integers in other imaginary quadratic number fields, it is possible to give upper estimates on the exponent, but its exact value remains...
Connect to the internet.
Whoa. Is that me? So its exact value remains an open problem, and I will explain later why that is so. What is the missing? What is the difference, or what is missing in order to complete this analysis? Another example I would like to give is a case where you have linear approximation rather than affine. So let's consider simultaneous homogeneous Diophantine approximation on three-dimensional space. We consider the left action of SL3 on F3 minus the origin. And SL3 also has a diagonal action on the product UF times UF, where GV comma W is GV and G inverse transpose W. And we consider the subvariety W alpha F, which is the set of pairs VW, such that JVW equals a fixed constant alpha, where JVW is the standard bilinear form, defined over every field. And so for a lattice gamma, as usual, we seek to solve the simultaneous inequalities gamma V minus V prime plus gamma inverse transpose W minus W prime less than epsilon, with the norm of gamma less than B times epsilon to the zeta, and VW, V prime, W prime in W alpha. So we are looking at the orbits. Of course, W alpha is invariant, and by its definition, it's invariant under this diagonal, or well, semi-diagonal action of SL3. Gamma acts on this invariant variety. It has almost sure dense orbits, and we want simultaneous approximation in a certain level of efficiency. And here we can let gamma be any lattice subgroup of SL3. Then kappa equals 5 over 2 for any F, R, C, or QP, and provided alpha is non-zero. Okay, but there's a big difference between this case and the previous case. Here we can state this for every, it really does not depend on gamma. It's the same rate. Okay, so one more example, which is also very classical. So it's the constant determinant variety. So we consider the variety of 3 by 3 matrices with a fixed determinant, non-zero. So VKF is X in M3F, such that the determinant of X equals K. And here we're going to look now at the group G equals SL3F times SL3F acting transitively on V via the usual action G1, G2X is G1X, G2 inverse. The stability group of the point X equals the identity is the diagonal subgroup H, such that H is in SL3. And H is the fixed point set of the involution G1, G2 goes to G2, G1, and hence V equals G mod H is a non-Riemannian symmetric space. And once again, for the fields, let's say R, C, or QP, and every irreducible lattice, this is of course a very important assumption, gamma contained in G, which is now SL3 times SL3, the exponent of Diophantine approximation of gamma on VKF is given by kappa equals 4/3 in all cases. And the best possible exponent, yeah, here there is a typo, I'm sorry. This is supposed to be, it's not V to F. I'm talking about the constant determinant variety of 2 by 2 matrices. So this last comment refers to 2 by 2 matrices. And for 2 by 2 matrices, the best possible exponent is kappa equals 3/2 for irreducible lattices in SL2 times SL2. But whether this is achieved in the dimension 2 case is an open problem again. And I will explain that, I'll try to explain that too. Okay, so how do we approach the computation of kappa? So we approach it in a fairly, I would say, typical way. We're going to have a general lower bound, which is going to be, which is going to apply in great generality. And then we're going to be able to establish a general upper bound. And we're going to have a criterion of when these two bounds match. Okay, so what about the lower bound? So lower bound for the Diophantine exponent. So a basic ingredient in solving the Diophantine inequalities, which approximate the point x0 in V, is to estimate how many orbit points gamma x are available to you in a compact neighborhood omega of x0 in the homogeneous variety G mod H. Ultimately, we have a point x0. We want to come near this point. And so we're going to look at the small compact neighborhood of this point x0. And we have to start by understanding how many points in the orbit gamma x fall into this little neighborhood. That's a very basic part of trying to prove a Diophantine bound. So we are going to define the empirical growth parameter for such points, denoted by A. We're going to take the sup over omega compact, and then we're going to take the lim sup of the log of the number of elements gamma in gamma whose norm is less than t, such that gamma x is in fact in omega. And we divide by log t. So there is such a number, whatever it is. This is the empirical, what you really find when you look at when these points in the dense orbit actually fall into this compact set. And it follows, so the estimates of this number is not a triviality, or the computation of this number is not a triviality. It follows from the work of Gorodnik and Barak Weiss that the rate of growth of such orbit points obeys the bounds which are satisfied by the volume growth of norm balls in the stability group H. So this is actually very intuitive, because if you think about G, take the connected Lie group, let's say R squared, and you should think about H in G as a line in the plane. And you should think about a little compact neighborhood of a point, let's say of the identity of the identity coset. If you lift it, you get a certain neighborhood of your line in the plane, and in G you get a certain neighborhood of H in G. And so intuitively, if you take this little neighborhood of the line or of H in G and you intersect it with a norm ball, then really the number of lattice points should be determined by the rate of growth of norm balls in H. So this is very intuitive, but it certainly requires a certain amount of work. And it's possible to show in great generality, as they did, that the number of points available for the approximation, the number of orbit points that fell into the neighborhood, follows this asymptotic volume growth of balls in H. So it's bounded by between these two numbers, t to the a and t to the a plus eta and t to the a minus eta, and this a can be calculated, or it's equal to the rate of volume growth of balls in H. That's the content of their result. Okay, so that's one ingredient. And now let D denote a bound for the local growth parameter of the invariant measure MV on the affine subvariety V in Fn. Namely, we look at the measure MV of a very small ball, V minus V naught less than epsilon, and we assume that it's greater or equal than C times epsilon to the D. Again, forgetting about the eta. So it has a certain lower bound on how the measure decays as epsilon goes to 0. And of course, for f equals r, this is simply the dimension of V. There's no mystery in this. But of course, if you have a complex variety, then it's the real dimension and not the complex one. What you really want is the rate of decay of the measure of small neighborhoods. So now, in general, in a compact neighborhood omega of x naught in V, there will exist an epsilon separated net of size roughly epsilon to the minus d. And that's the significance of this number. So if you think once again about the plane, for example, then this becomes really quite obvious. And really, this is a completely local problem. We are looking at a neighborhood of a given point in a variety. So this is the size of the epsilon separated net that we are going to have. And now there are at most t to the a plus eta pigeons, namely points of the form gamma x in omega whose norm is less than t, and roughly e to the minus d pigeonholes, namely disjoint epsilon balls in omega. So if your Diophantine approximation process in omega was successful, then clearly you had more pigeons than pigeonholes. So epsilon to the minus d is less than or equal than t to the a plus eta. And so t is at least epsilon to the minus d over a. And that means, of course, t was the size of the norm ball of the matrices. So we have the following statement. D over a is a lower bound on the Diophantine exponent kappa. it is impossible to approximate points on V equals G mod H by points in lattice orbits any faster, namely using matrices of smaller norm. So you can see that this is a very general argument. It has nothing to do with algebraic groups, of course. Okay. So the question is now, of course, is how do you match this bound? And to derive an upper bound on the Diophantine exponent requires other considerations. Namely, we're going to require spectral estimates leading to a quantitative mean ergodic theorem. And having these spectral estimates and the mean ergodic theorem at our disposal, we're going to use some dynamical arguments exploiting the speed of equidistribution. So just as a matter of philosophical, I don't know, point, one of the utilities of a quantitative mean ergodic theorem is that it tells you that the points on which you average distribute themselves in the space evenly. And if you have a quantitative estimate on this, then you will say that they distribute themselves in the space with a certain speed. And you can exploit certain dynamical arguments using this speed. And for those who are familiar with this is really a version of, a quantitative version of the shrinking target methods in homogeneous dynamics. Yeah. So some people in the audience are very familiar with that. So the first thing we're going to do is to state, I'm going to state the quantitative mean ergodic theorem that we want. And it's as follows. Consider the intersection of norm balls with a stability group H, namely, HT is going to be the set of H in H whose norm is less than T. And we consider the invariant probability measure M on Y equals G mod gamma. And we are going to define averaging operators pi y beta t acting from L to G mod gamma to L to G mod gamma. And they are going to be given by the following average, which is really the analog in our case of the classical von Neumann or Birkhoff averages. We consider a point y in our space. Whoa, that's a challenge. We consider a point y in our space y, which is G mod gamma. And then we translate the point y by elements H, which are taken in a norm ball. So we move along the orbit of y under H, but we filter the orbit according to the norm balls. And then we divide by the measure of this ball. So this is an averaging operator which is very similar to the classical averaging operators. And we are now going to assume that the quantitative mean ergodic theorem for the averaging operators pi y beta t holds. And by that we mean that there exists theta such that if you consider the difference between the averaging operator at the point in the orbit, at the point y, so this is a certain function, and you compare it to the average over y over this function, and classically, of course, one would call this the time average of f, and this will be called the space average of f. So this difference converges to 0. This is the ergodic hypothesis, if you like. That's the content of the ergodic theorem. But not only it converges to 0, in fact, it decays. The operator norm of this operator decays like a power of the volume of HT. So those who are familiar with the classical ergodic theorem will recognize that this is a very powerful statement. One, because it deals with the operator norm which is never the case in classical ergodic theory. And second, because you have a very good decay estimate which is given by a negative power of the volume. So this is a very good mean ergodic theorem. And it turns out that the foregoing estimate holds in great generality. And the reason for that is that the representation of G in L2 naught G mod gamma typically has a spectral gap. And that's a manifestation of it. Okay, so once G mod gamma, L2 naught G mod gamma has a spectral gap, it follows that any non-amenable closed subgroup H has the property that the unitary representation of H in L2 G mod gamma also has a spectral gap. And remember, or maybe I should emphasize this point, which is going to come back later and it's going to be very important. Notice that we are talking about L2 G mod gamma, but our averaging operators are supported on H, on a subgroup, maybe a very small subgroup. We are looking at the restriction of the representation of G in L2 G mod gamma to a maybe small subgroup H. Okay, so now, so any non-amenable closed subgroup H will also have a spectral gap if G does, and G does, typically. And so now suppose that H is, for example, a non-compact simple subgroup of G. And then the spectral gap implies the estimate stated above on the operator norm of pi y beta t. So what I'm saying, and there are many other cases where such an estimate holds. So basically what I'm saying in this statement is that this estimate, which is the crucial estimate that we're interested in, is actually very, very common. Why is it so common? Because the action of G on G mod gamma has a spectral gap. And if the action of G on G mod gamma has a spectral gap, then the action of a closed subgroup, which is non-amenable, also has a spectral gap. And typically, this would mean that you have a decay estimate which is given by a certain power of the volume. Although, of course, it's not completely universal, but it's very common. It would be true for example, as it is stated here, it would be true for any non-compact simple subgroup. So now the question, okay, so now one more remark is that the quantitative mean ergodic theorem for the averaging operators, pi y beta t, is a much stronger statement, and it implies, of course, the ergodicity of H on G mod gamma. So a group that satisfies the mean ergodic theorem is ergodic. That's the easy implication. And if H is ergodic on G mod gamma, then by the duality principle for homogeneous spaces, the ergodicity of gamma on G mod H follows. So in particular, almost every gamma orbit in V equals G mod H is dense. So for those who are familiar with the representation theory of semisimple groups, then because of the decay of matrix coefficients, then ergodicity and even mixing is very, very robust. And so the issue of ergodicity of gamma orbits in G mod H is really not an issue. Okay, so now we're ready. We have all the ingredients to state an upper bound for the Diophantine exponent. So let G be, in GLN, be an algebraic group defined over F, and H a Zariski closed unimodular subgroup, and gamma a discrete lattice in G. And we restrict a norm on M and F to G and assume that HT, so these are the norm balls restricted to H, satisfies the volume growth bound with rate A. Notice that this is an assumption only on age. It simply says that the volume growth of norm balls in age is essentially has parameter rate A. So once again, it's very general. And let D denote a bound for the local growth parameter of the invariant measure on the affine variety V equals G mod H. So there is such a number. In the real case, it's simply the dimension. And assume that the averages beta t supported on ht satisfy the quantitative mean ergodic theorem in L2 G mod gamma with rate theta. And as I tried to convince you in the previous two slides, this is a very general situation. Once again, because G has a spectral gap on G mod gamma, so subgroups of G, H, will also have a spectral gap on G mod gamma. So this is a very general phenomenon. So under these conditions, under the assumption stated above, the Diophantine exponent satisfies the upper bound. Kappa is less than or equal than 1 over 2 theta times d over a, the same d over a that we had before. And so we are using spectral methods, and so there's a spectral parameter that comes into the upper bound. But notice that if 2 theta equals 1, then the lower and upper bounds for the Diophantine exponents coincide. Yes?
So D here is the dimension of D, or what is local dimension?
Well, for example, D is the rate of decay of the measure of small neighborhoods. So if you have a complex variety, then you don't use the complex dimension. You have to view it as a real variety. So it's the rate of decay of little neighborhoods, of the measure of little neighborhoods. So it's the real dimension for, it's the real dimension. In the p-adic case, yeah, okay, it's, yeah. So the right way to refer to the real, the complex, and the p-adic is to say it's how the local measure decays. Okay, so what does this mean? What does this mean that 2 theta equals 1? So going back, you can see it means, of course, that theta equals 1/2. And what you can see here is that this means that the rate of decay in the mean ergodic theorem is like 1 over the square root of the volume. That's what it means for the ergodic theorem.
That's the best possible fit.
Yes, that's what we're getting at. So 2 theta equals 1 implies theta equals 1/2 implies in the mean ergodic theorem we have decay 1 over the square root of the volume. So can we get decay which is as good as that? And so, so the corollary that we have is that if the rate of convergence in the mean ergodic theorem for the averaging operators beta t acting on L2 G mod gamma, if this rate of decay is as fast as the inverse of the square root of the volume, then the rate of Diophantine approximation of gamma orbits on the variety V equals G mod H is best possible. And the Diophantine exponent is given then by kappa equals D over A, the a priori pigeonhole bound. So how do we realize this decay? So, for example, if the stability group H is semi-simple and non-compact, and the restriction of the automorphic representation pi G mod gamma to age is a tempered representation of age, then the Diophantine exponent of the irreducible lattice gamma of G in its action on G mod age is best possible. and again, n given by d over a. So what I'm giving here in this statement is a very well-known criterion of when it is that you can realize decay which is as fast as the 1 over the square root of the volume. And the way you can realize it is to ensure that the automorphic representation of G, when restricted to age, is a so-called tempered representation of H. Okay, so tempered representations of age, these are those representations of age which are weakly contained in the regular representation of age. And these are the representations that has the fastest possible decay. Okay, and basically what we've done here is to say that if you have the fastest possible decay for a semisimple group, then on the variety that it defines, so if you have best possible decay for age in the representation on G mod gamma, then when gamma is going to act on G mod age, you will have the best possible Diophantine exponent. Okay, so now I would like to make the point that it's really quite surprising and it's very useful that this condition of subgroup temperedness holds in considerable generality for a large class of triples, GH gamma. So everything I said so far, I never really showed you even one example where this happens. Okay, so what I would like to do now in the 3 or 4 minutes that I have left, I want to say that there are many examples where the restriction of the automorphic representation on G mod gamma to a subgroup H is in fact tempered as a representation of H. And it's actually quite robust. We were really quite surprised by this. And the examples that I had in the introduction are designed to demonstrate these principles. Several general principles which can be used to establish subgroup temperedness. So the first and the easiest to work with is Kazhdan's original argument. So if you recall, Kazhdan's original argument basically showed that if you look at the group SL2R, semi-direct product R2 contained in G, any G, then any unitary representation of G without R2 invariant unit vectors is in fact tempered when restricted to SL2. I mean, this sometimes goes under the name of relative property T, but actually in Kazhdan's original argument, he doesn't just show that SL2 has a spectral gap. In fact, he shows that the representation of SL2 is weakly contained in the regular. Namely, it's tempered. So this means, for example, that you can take your favorite algebraic group, or, well, any group, and you can embed age in it. For example, you can embed SL2 semi-direct product R2 in SLN for a very large n. It would still be the case that the restriction of the automorphic representation of G to this subgroup H is tempered as a representation of H. So the Diophantine exponent on the homogeneous variety G mod H would be best possible. For example, on the variety SL3 modulo SL2, where SL2 is embedded in the corner, you have best possible approximation. So Kazhdan's argument can be used. Okay, so there's a number of things you can do with this, but okay, that demonstrates the principle. And maybe I'll just finish this page. So when G is semi-simple and has property T, there are bounds on K finite matrix coefficients of G in general unitary representations. And these can be restricted to a subgroup H, and they are often, in fact, in L2H. That's much more general than at least I realized. It's really very common. It's quite surprising. And so you get a very large collection of tempered subgroups from this principle. For example, and this, okay, so this holds for the images of all the irreducible representations of SL2R in SLN. This was a fact noted and used by Margulis already in 95. But it's much more general than that. And finally, unitary representations of semisimple group have matrix coefficients in L2kg for some k. Also a very well-known classical fact in representation theory. So this means that if you restrict a representation of g to the k to the diagonally embedded copy of g, this will give you matrix coefficients which are in L2 plus eta g. So the diagonally embedded group is in fact tempered. And if you remember, we had a diagonally embedded group, for example, SL3 embedded diagonally in SL3 times SL3. This was the structure of the constant determinant variety. And finally, and that's just to explain the remarks I started with, for some lattices and their low-level congruent subgroups, the Selberg eigenvalue conjecture is known to hold, so that L2 G mod gamma is known to be a tempered representation of G, which is a much, much more stringent condition. And this holds, for example, for SL2Z in SL2R and for SL2ZI in SL2C, but it's not known in general. So that accounts for the fact that sometimes we can do Diophantine approximation in the real or the complex plane by Gaussian or Eisenstein integers, but not by other integers because we don't know this spectral gap, although it may well hold. Okay, so thank you very much for your patience.
So thank you very much. Other questions?
So, the lower bound is slightly in the Dirichlet theorem.
In these, sorry?
Dirichlet theorem.
Yes.
So that's the same thing. Okay, so your assumption on the field, on your current field, was characteristic 0.
Sorry, I didn't.
Did you add? Do I really need to use that?
Oh yes, because that's I was told you need.
Yeah.
Yes. So it's your local field F as characteristic is it assumed to have characteristic 0 or not?
Well, I mean, as you saw, this is not. This analysis is really quite robust. Probably not, but we've never really gone through all the details. You need some spectral input. The geometry is really very primitive. You don't really need much. So if you're looking for algebraic groups over fields of characteristic, positive characteristic, then I would assume that most of this analysis goes through. You can formulate it in completely general terms for every locally compact group. The bars you have to meet is that you have something of a solution to the lattice point counting problem in H. And then you have the local dimension of the measure. And then you have the quantitative mean ergodic theorem. And if you have these three ingredients, then all of this analysis goes through.
And when H is, instead of being simple, say minimal parabolic. So if you want to do Diophantine approximation on flag manifolds, for instance.
Minimal parabolic, yes. You can give an upper bound, but a minimal parabolic is amenable.
Yeah.
And that's, okay, so that's a huge constraint. We need the spectral gap.
So do you have other methods to tackle this case?
You can get a bound. You can get an upper bound, but you can in this method you cannot possibly get the best possible. Yes, but you can get an upper bound. Yeah, definitely.
Other questions?
How do you get an upper bound in this case?
Well, I mean, this is really just a situation where I mean, we tried here to keep very close track of the constants, but actually this is an instance of a more general duality theorem. So, I mean, basically, I hope it was clear from what I said that there is a duality here. There is the representation of H on G mod gamma, from which you want to derive consequences for the action of gamma on G mod H. And this can be done in much greater generality, and you can even have equidistribution theorems, which you can prove quite generally. And what you would have to do, you would have to argue in Sobolev space and prove a mean ergodic theorem with a rate in Sobolev space, and from this you will derive some upper bound. There's going to be a lot of compromises on the rate, but it will produce some upper bound. Maybe, if I'm allowed one more sentence, one very interesting problem here is to go in the other direction. So everybody is always looking for ways to prove a spectral gap rather than use it. And it's a very interesting question whether, if you know for some completely different combinatorial considerations that you have best possible or even very good Diophantine approximation on the variety, can you derive then a spectral bound in the automorphic representation? So this is definitely a problem that is worth thinking about, but we don't have any results along these lines.
Just one question. Do you think it's there is some hope to classify somehow, I don't know, algebraic subgroups which are tempered, I mean, in the sense, or embedded as tempered subgroup of G?
Classify, I don't know, because it comes from several different, completely different techniques. For example, every irreducible representation of SL2 in SLN gives you a tempered subgroup. And now I've worked on it with a graduate student of mine. If you take SL3, then all irreducible representations of SL3 in SLN are tempered except 2. And it's very easy to make the I mean, you can make the computation and see why that is true, but that doesn't bode very well. I mean, if you want to consider, you know, SLK and SLN, you're going to go through a very complicated computation. There's going to be a finite set of representations which are bad. All the rest of them are going to be good. So a classification that would be, even in this particular case, SLK and SLN,
Thank you.
thank you very much.